Let's understand mechanical energy in this video. Have you ever wondered why a swinging pendulum keeps moving? Or why a raised rock can hit the ground hard when dropped? These everyday events are about how energy moves between motion and position. Mechanical energy is the energy an object has because of its motion or its position. It has two parts: kinetic energy, which comes from motion, and potential energy, which comes from position. Kinetic energy is the energy an object has due to its motion, and it tells us how much work the moving object can do. The formula for kinetic energy is Ke equals 1/2 times mass times velocity squared, where mass is in kilograms and velocity is in meters per second. For example, a 1 kilogram object moving at 1 meter per second has Ke equals 1/2 times 1 times 1 squared, that is 0.5 joules. In the SI system, kinetic energy is measured in joules, and 1 joule equals 1 kilogram meter squared per second squared. Kinetic energy depends on mass and on the square of speed. So if speed doubles, kinetic energy increases by 4 times. Potential energy is the energy stored because of an object's position or configuration. For gravitational potential energy near Earth, we use U equals mgh, where m is mass, g is 9.8 meters per second squared, and h is height above a reference point. A stretch spring stores elastic potential energy, and for springs, the stored energy depends on how far the spring is stretched or compressed. These two energies can change into each other. For example, a pendulum converts potential energy to kinetic energy and back as it swings. Also, when only conservative forces act, the sum of kinetic and potential energy stays constant. This is the conservation of mechanical energy. Now let us look at a solved example to see this in action. Question number 1 asks, a mass of 2 kilograms is suspended by a light string of length 10 meters and given a horizontal speed of 50 meters per second. Find its speed at point B. Step 1. Compute kinetic energy at point A using Ke equals 1/2 mv squared. So K at A equals 1/2 times 2 times 50 squared, which equals 2500 joules. Step 2. Note that when the mass rises by 10 meters, its potential energy increases by mgh, which equals 2 times 9.8 times 10 equals 196 joules. Step 3. Total mechanical energy is conserved. So K at B equals K at A minus the gain in potential energy, that is 2500 minus 196 equals 2304 joules. Step 4. Solve for speed at B from Ke equals 1/2 mv squared. Substitute numbers. 2304 equals 1/2 times 2 times v squared. So v squared equals 2304 and v equals 48 meters per second. So the speed at point B is 48 meters per second. Next solved example. Question number 2 asks, the potential energy U equals ax squared minus bx, where a and b are positive constants. Find the equilibrium position and its stability. Step 1. Find equilibrium by setting the force to 0. Force equals negative du by dx. So set b minus 2ax equals 0, which gives x equals b divided by 2a. Step 2. Check stability by looking at the second derivative of u. D squared u by dx squared equals 2a, which is positive. So u has a minimum and the equilibrium is stable. So the equilibrium position is x equals b divided by 2a, and it is stable. So what do we learn from this? We learn mechanical energy is the sum of kinetic and potential energy. These forms convert into one another, and for conservative forces, their total is conserved. Let us quickly remember the main points. Ke equals 1/2 mv squared, v equals mgh for gravity, and conservation means K plus V stays constant when no non-conservative forces act. Keep practicing examples like pendulum motion and energy surfaces to build intuition about minima and stability. Thank you for watching. Keep exploring and solving problems. And do check more lessons on EduRev for clear notes and practice in a friendly way.